It's a great honor to be speaking at this conference. And I can testify that even though I am not in the direct mathematical lineage of Tate, that his influence goes much further than the 900 plus names that were on yesterday's slides. And in fact, only recently have I come to appreciate how important his influence was to my mathematical grandparent, John Coates. And I'm sure that I know that Coates would have loved to have attended a conference like this. And what I'd like to do, or hope to do in this talk, is also to show that not only did Tate sort of open the door to this beautiful beautiful landscape that we've wandered through this week, but that he also sort of gave us the map to sort of particularly interesting viewpoints. And so, although I did not coordinate in any way with the previous speaker, I could not have been better set up with his remedial course. So I'm going to start where Frank led us. Okay, so let's let F be a number field. And I'll denote just for the moment. So be interested in the Galois cohomology of absolute Galois group of F. And let's say that it's acting on some module M. And I'm going to assume that this is a torsion module. In fact, I'm going to always fix a prime P and make it a Z mod P to the NZ module. And the action is always going to be continuous and unramified away from finitely many places from a finite set of primes of F. And we're going to be interested in the Galois cohomology of such modules. This is a huge group. And so to get anything interesting or tractable, we need to cut it down. And in fact, we're going to cut it down by looking at a collection of classes that satisfy conditions that are given sort of locally at all primes. So we want when we localize at a prime V of F, the class C, I want to require that it lands in some subspace or subset, some module of the local version of this. And so we're going to look at something like this, and I'm going to call that H1, the script L of F of M. And now let me tell you what those L's are. All right. See if I can stay out of the shadows. So script L is just this collection of submodules of the local cohomology groups, with the completions at V of M for all places M. And what we need is that LV is the unramified condition, or the set of unramified classes for all but finitely many places V. And I've already made my first mistake because I'm writing on the backboard. I thought I had this well planned out. So we look at a collection of such places indexed by the places of V, and we look at modules like that, and that's going away. So we have these local conditions, and let me give you some examples. Maybe the first example of interest will be M is just Z mod P to the N with the trivial action. And LV, then the unramified condition at all places. Then look at H1F of M. that's just the homomorphisms from our Galois group to M. So already it factors through the abelianization of the Galois group. And then we have the condition of being unramified at all the places. So that's just the set of homomorphisms that are trivial on all the inertia groups. That's an inertia group. And so that's going to factor through the maximal abelian unramified extension of F, right? Because this is really Z-mod on P to the N. And that's, of course, by class field theory, just the class group. And so we're just looking at the homomorphisms from the class group of F to Z-mod on P to the N. So we're capturing the P to the N part of the class group. You might be more ambitious and okay, so that's and want to look at more interesting modules. And so the other thing we've seen in a talk earlier this week, we might take E over F to be an elliptic curve. And take M to be the mod P to the n torsion that also carries an action of the Galois group unramified away from finitely many places, the places of bad reduction, possibly P. And then we can let LV to be just the image of the local points on P to the n under the analog of the Kummer map. And the corresponding global group is just the usual P to the n Selmer group of the elliptic curve over F. So this example's disappearing in a moment. And yeah, so these are two sort of probably the examples I would like to say the most about, but the ones that I can probably say the least about. So I will be talking about other examples as we go forward. So what I want to begin by saying is that Tate duality provides a tool for getting a handle, perhaps, or at least an idea for getting a handle on these things. And it was alluded to in Frank's talk in this formula that he attributed to Greenberg and Wiles, which comes out of Tate global duality. And so what it begins with is we say we want to study this H1L of F of M. And what I'm going to try to do is capture classes in here maybe by looking at their restrictions in a subset of these places where I'm just going to simplify the situation, and where I've imposed that unramified condition. So like in the case of class groups, every element of the class group is represented by an ideal, a prime ideal even in the field. And so you can sort of capture it by restricting or looking at its image under the localization map at those primes. And if you're lucky, you can choose this set. Well, maybe you can even get an injection like this. And so now you want to know what's the image. Let's call this map alpha. And how do we get a handle on that image? So it turns out you can look at a Selmer group for a dual module, M star. So what is M star? M star is going to be, well, it's sometimes called the Tate dual. So it's going to be, in this case, it's going to be just the homomorphisms from M into well, in this case, it's just mu pn, but more generally into the roots of unity with the Galois action. Good. So you can have a corresponding Selmer group. You can look at the dual Selmer conditions, which are just defined by looking at the spaces that are the annihilators of the ones you've chosen here under Tate local duality. So you use the local duality to provide you some conditions. And now what I'm going to do is not quite take that. I'm going to relax the conditions at these sets. So L star is a collection of LV star. This is the annihilator of LV if V doesn't belong to S. And in fact, I'm allowing it to be anything we want at the primes in S. And then just remember what that is because it's getting in my way. And then we look at what we've added. What was the difference between the sort of this relaxed condition and this dual condition? So that would have been, well, there was anything that we added, and the stuff that was sort of old before we relaxed this condition was the unramified classes. On this, we can identify with the restriction to inertia, so fixed by the local field. And the nice thing is, when the Galois action is unramified in M, this is a very, very easy object to compute. This is also a very easy object to compute. This is identified with M divided by the action of the Frobenius minus 1. And this is identified with almost the same thing. The homomorphisms from, well, actually from mu pn into M star fixed by the Frobenius at V. And the point is that local duality gives us a perfect pairing here. So there's a perfect pairing into QP mod ZP here. So this is perfect pairing. That's what we have. So the idea is if we're lucky, we can choose a nice set of primes where everything is unramified and we've captured the whole object that we're interested in. At the same time, if we can understand the image of this map, maybe we can use this duality to get something interesting. And the point is that the image of alpha and the image of beta are mutual annihilators. So if you've controlled one, then you've controlled the other. Maybe it would help to think of just one prime. You start off with a class here. You want to say something about its size. What's its order? You find a prime so that when you restrict to that prime, just what it is on Frobenius, it gives you something of that order. If at the same time you could have constructed an element here in ramification and see that ramification was large for some reason related to the situation that you're in, then you would have bounded the possible size of your original element. That's it. So this is, in fact, the idea of Euler systems. Find ramified classes which you can use to control the size of unramified things. So we already saw this a little bit in Frank's talk. So if we go back to example 1, so what is M star? M star is just mu p to the n in this case. And by Kummer theory, we have that an identification of F star modulo its p to the n powers is h1f of mu p to the n. So what we want to do is maybe write down some explicit elements here in whatever setting that we're working in, such that we can recognize when things are ramified, and that was precisely the kind of thing Frank was talking about when you look at the valuation of the element alpha and f. You're looking at a field that comes from taking the p to the nth roots of or p to the nth root of alpha, and trying to study its ramification. And you can, in this framework, you can recast all the kind of classical results for cyclotomic fields. Stickelberger's theorem, Herbrandt's theorem, theorems about class groups of cyclotomic fields can all, the proofs, many of their proofs can all be recast in this sort of framework. It's not new proofs, it's just another way of thinking about them. This example, well, the dual module for the elliptic curve, or the p to the n torsion points of the elliptic curve, is itself. So there's nothing new. Here, we went from the trivial module to the roots of unity, and we picked up an interesting description of the dual Selmer, or the dual cohomology group. Here, passing to the dual doesn't give you anything new to get your hands on. And so I think it's actually kind of an interesting and hard problem to directly write down ramified classes and for the elliptic curve. And I'll try to return to that later. Maybe I should say, if there's any confusion or about what I'm saying here, now would be a good time to ask your question. I want an extra product sign on the board. Yes, I do. Thank you.
You're making these observations about Galois cohomology, but can you say you want to use like one mean unramified to understand the other one? But what's sort of the goal? I'm a little lost with the goal of what you're trying to do.
Right. So that's because I skipped that one slide, which is that one of the fundamental, or many of the fundamental problems in algebraic number theory are ask about sort of the size of various arithmetically interesting groups, class groups, Mordell-Weil groups, Tate-Schaffer-Ravage groups, K groups, extension groups of motives, and all of those have either a formulation in Galois cohomology or at least a reflection in Galois cohomology. And so so what I'm actually trying to do is to get a handle perhaps on the size of this object. Thanks. Yeah.
When you say in two that it's its own annihilator?
Yes.
That's like with the particular L that you've chosen, right?
Well, the module, no, I didn't say its own annihilator, its own dual. The module M is its own dual, M star, yeah. And it is, yeah. And what's hard is to write down ramified classes for that. And like passing the dual, I haven't changed anything. So,
I thought
yeah.
So what one was meant to do is like change this L condition. So on one side you make it more strenuous, and then on the other side you control.
Yes, but there's no particular reason to pass to the dual if M is itself, right? I mean, and all I'm saying is that unlike the trivial module, when we pass to the dual, we don't get anything new to get our hands on. All right. So, in fact, there are very few examples that I know of where we are successful in just writing down ramified classes without passing through some more auxiliary constructions. There is basically the case of the Stickelberger's theorem when F is an abelian extension of Q. There is this remarkable theorem of Flock, which is like the example 3, where I take M to be the add 0 of maybe the p to the n torsion points, which I mean, we take the Homs from this object to itself modulo the scalars. And maybe I should say more recently, there have been constructions of what the bipartite side of bipartite Euler systems, which use cycles in the mod L reduction of Schmor varieties to produce other situations where we can at least recognize cycles or classes as being ramified. That, just as an aside, is in the context of the Gann-Gross-Prasad conjectures and its arithmetic formulations often. And those three names, I think, are all descendants of John Tate. But I'm going to revisit this situation, and I'm going to give you a very general construction of some ramified classes that recovers and generalizes most of the known results here. So I'm going to first give you something optimistic, and then I'm going to tell you something kind of pessimistic, and then we're going to try to be optimistic about something else as time permits. So I want to particularly revisit this. So the question is, where should we look for cohomology classes that have some kind of ramification in them? Here we write down, in this case, we're writing down explicit elements in number fields. And in fact, in the case of Stickelberger's theorem, you write down a bunch of Gauss sums and you analyze their factorization. What I'm going to do here, maybe try to say a few words. So suppose your module M has some kind of geometric origin. And what do I mean by that? So suppose that there's some variety over your number field, X. Maybe it's smooth and complete. And then we can look at its cohomology, say tall cohomology maybe. P to the n. And let's say our M is a quotient or a subquotient or something like this. So that's then where might we look for Galois cohomology classes? Well, one way to think of cohomology classes in objects in H1 F of M are as extension classes. So a class in H1 Fm is just the class of an extension. Maybe in this case, I can do looks like this. Injection. So an extension in the category, say, of Z mod P to the n GF modules. Very concretely, if I took an element here, if I went to 1, my cocycle is just C of sigma is sigma of E minus E, which is an element of L. So maybe instead of trying to write down cohomology classes, I can look for extensions. And in this context, one finds a lot of extensions, maybe in the cohomology, the interior of X. So I might take a closed subvariety and remove it. I might be looking at H star F, H star of U. I'm going to forget the coefficients. And maybe, let's say this is codimension then C. So there would be star minus 2C if everything is smooth, and then a minus C twist. So I'm not writing coefficients here. Usually I'm just going to be Z mod P to the n. If I put something like this here, it's the Z mod P to the n with the minus minus C, or Tate twist. And if we're really lucky, let's see if I can make this. That's not so smart. If we're very fortunate, maybe Z is a lot simpler, and we could write down some class inside here with a very nice, simple Galois action. So maybe there's a Z mod P to the N just sitting inside here, because we can write down a class. We pull that class back, we would get some extension E, and then we push forward. That's a very, very explicit way of thinking about how to find extensions in the cohomology of the interior. And so let's do that. All right, I'll do an example. So let's say I have an elliptic curve over Q, so it has some modular parameterization. I'm going to take X to be, I don't know what is writing there, 2 copies of this modular curve. And I'm going to pretend that I can embed in there a modular curve where I've added a prime L to the level, which I'm going to call that X naught as X. This is just the graph of the Hecke correspondence. So on one factor, its tau goes to tau. On the other factor, it goes to tau to L to the tau. And I'm lying. This is not a closed embedding. I might have to blow up some cusps to make it actually embedding, but that's going to be completely innocuous, because blowing up cusps is just going to add P1s, and the cohomology of P1s are not going to interfere with the cohomology that I'm interested in. So we're just going to pretend that we don't have to do that. And you'll see that this method works without, you don't have to use modular curves, and so this is kind of just the annoying case. All right, so I'm going to, I need to find well, maybe I should say, what are we going to look at? Here we're going to look at the H2 of X over F bar, and that will have as a quotient, by the Kunith formula, I'll have as a quotient the x1 of x0 of the modular curve, tensor x1 of the modular curve. I can project down to the elliptic curve. So I'm going to have as a quotient, well, I will actually have the add 0 of my elliptic curve, maybe mapped to that, with a twist. And the twist is probably a minus 1 twist. And now in this I have a my codimension is 1, my z is my x naught. So I want to find some element in H1 of x naught that has some nice, reasonable Galois action. So in here. And we're in H1. So I'm going to look at a situation where say p to the n divides L minus 1. Then I have a nice cover of this curve, x1 of n. It's still x0 of n here, and x1 of L. So maybe just I'll write gamma 0 of n intersect gamma 1 of L. So this is a z mod LZ cross cover. I have as a quotient a z mod p to the n cover under this hypothesis. And so this I can think of as giving me a class in H1 of x naught. Over F bar, z mod p to the n, which is almost the right twist here. And so I just twist everything away with on the other side, and I probably have had the wrong twist here, because eventually if I put a 1 here, I should have had that. And so this class by this procedure then yeah, okay. Let me.
What is it looks like stars. 2 minus 2c has to be equal to 1.
I'm sorry, because this is 2 minus 2c plus 1. This is the Giessen sequence, and yeah, okay. It's kind of important. Two minus 2 plus 1. And so this class here, we can hope, pulls back to an extension like this. What we need to know is something about the surjectivity here, and maybe the injectivity at this stage. The surjectivity here is at least holds up to an exponent that depends only on the curve x and not on the choice of the prime L. So this is so up to some error that you can control. This is perfectly fine. And the injectivity here is also okay in this case, because the image for us in this particular situation would be coming from the H0 of x naught, and that's not going to interfere with our quotient to there.
So what does H2 of U agree with Ed0 of E P to the N?
So it's not saying this agrees. I'm saying if we project to the elliptic curve, we can project under this map, we have a map to EP to the N, we have a map to Homs from E to EP to the N. You have to use the fact that, right. I'm not saying it's a surjection either. But there's a map. Let me say, okay, so there's a map. We have H2 of x squared to the H1, maybe with the 1 here, to the H1 of x, tensor H1, 1 of x with the 1. We can think of this as now Homs from the H1 of x to the H1 of x. And I can find the quotient of my p to the n torsion of my elliptic curve is a quotient of this, and I can also map it into there. And so I get a map 2 here, and you might ask, what's your index inside there? And a congruence number or a degree of the modular parameterization will show up. Does that answer the question?
Yes.
Okay, yeah.
Very helpful.
Please continue to shout at me. So what we have then is this L. We have the class of this extension in H1 of Q. In this case, my F is going to be Q of the add 0 of the modular curve. And now we just need to ask, what are its ramification properties? So this is a class maybe with an L here. Away from the primes in N, the prime P, and the prime L, everything can be sort of done over the ring of integers of the local field, ZQ. This gives unramified classes. Everything is smooth and proper, fine. I'm mostly interested in the prime L. I want to claim that we actually get a ramified class, that it's not an unramified situation. So where's the ramification? The ramification is starting to appear in the bad reduction of this curve. This curve over the finite field to elements. It's famously sort of a union of two copies of x naught of n intersecting transversely at supersingular points, one classifying multiplicative subgroups away from the intersection, the other one classifying étale subgroups of order L. The curve x1, we add the gamma 1 of n structure over it, we're getting a cover It's atal over one of the components, but it's tamely ramified over the other. And it's that tame ramification that gives us the ramification for this class. So when you chase through the definitions, you discover that you can actually describe the restriction to the inertia group at L precisely in terms of that tamely ramified extension. And it's a totally tamely ramified extension. And indeed, you find that this class is, when I restrict to the inertia group at L, I'm thinking of this as sort of homomorphisms from H1 to H1 at the prime L. And what you end up with is the correspondence associated to that component where it was ramified. And that, in this setting, is just the endomorphism. That's the Frobenius at L. So you have a completely explicit description of what that inertia is in terms of the Galois action on the elliptic curve. And of course, that will, or on the modular curve, and that will project down to something on the adjoint. And once you have those classes and that complete description, you can run the argument that I sketched. Choose the right set of primes using some glorified Chebyshev density argument, and not so much bound the size of the summer group, but you can at least produce an annihilator. And you can show that up to some error that's going to reflect whether or not the image of Galois here is surjective or not, and a few other things. You will actually have annihilated the corresponding summer group by the degree of the modular parameterization, which is just the controlling what's the index inside here, the failure of this map to be surjective. There's nothing special about this for modular curves. So I can run the same argument with x replaced by a Shimura curve. So you can look at the elliptic curves parameterized by a Shimura curve, and I don't even have to blow up any cusps. You get the same you get a collection of classes, you run the same thing. You can do this for Shimura curves over totally real fields. So for elliptic curves that are modular, or at least parameterized by a Shimura curve over a totally real field, you can give quantitative results on the annihilation of the Selmer group that's ad zero in terms of the degree of that modular parameterization. This same geometric picture, though, also holds for Shimura varieties associated to groups, so you have the type UN, 1. And using this, you can also construct classes that annihilate the adjoint Selmer groups for the regular algebraic self-dual conjugate cuspidal representations of I guess, GLN plus 1 over a CM field. So you can recover theorems. I mean, so far, actually, I'm not proving a new theorem, at least not a qualitatively new theorem. I'm giving new proofs of theorems due to a number of people at Wiles, Taylor, Wiles, Cousin, ending most recently with work of Newton and Thorne. But I'm also recovering quantitative versions of these theorems, which seem to be new in many cases. So here's a very simple way of writing down some ramified classes. And I should say this so far has been joint with, actually, Venkatesh. It's been kicking around for the last 6 years. If anybody knows the two of us, neither of us is good at writing quickly, I think. All right. So that's kind of an optimistic. Great. Here's a really simple way of writing down some ramified classes, and it seems to apply in a lot of situations. But I don't think it can go beyond this. I think there's actual reasons on the representation theory side to say that this at least this particular argument is limited to adjoint representations. So even if you tried to work with sort of more complicated Shimura varieties, and maybe you, instead of taking products like this, you were taking some sub-Shimura variety inside another, you're really only going to see adjoint representations this way. So that was the positive, then the negative. Now I should say something positive again, right? So, okay. So despite this situation, we're not so good at finding ramified classes. But what we do know, thanks to work that began with Coley-Wagen's exciting breakthrough on elliptic curves, and maybe the work of the theory of Euler systems, which he initiated and then was developed by Carl Rubin and others. We know that if we have some way of constructing some sort of systematic classes of unramified extensions, but that they live and begin life really over ramified extensions of the base field, then we can, through a process often known as the Coley-Wagen derivative, take those unramified classes and produce ramified classes. So, okay, we're better at detecting things are unramified, right? The criterion of Neron, Ogschafer, Rabich, and things like that. So maybe instead of looking for ramified stuff, I should start looking for unramified things. So now the question is, where should I go looking for unramified things? Let me try to tell you where I've been looking for them, at least. So there's a philosophy, and now I'm going to pass from mod p to the n cohomology to, say, QP or integral cohomology, like ZP cohomology. So there's a philosophy that sort of emerges from the Beilinson and the Bloch-Kato conjectures that that we should have extensions with like this when the coefficients are QP only when some L function is vanishing. So we should use that as a guide. And also, there's my philosophy, which is the only time I'm going to be able to write down an extension like this is that there should be a unique extension that I can find if I'm going to write it down. And so there's probably only I should be looking for the case of a simple zero. At least that's the first situations to look at. So you look at cases of simple zeros. And what are the situations with the easiest situations with simple zeros or to detect is usually when the zero comes from the gamma factor of the L function. So from the Archimedean part of the L function that appeared in Michael's talk on Tuesday. And so I'm sort of, for me, I start with some kind of representation of the L function that I'm interested in. The L function of some automorphic form, but that automorphic form has an expression in cohomology. And then I try to find the corresponding extension in some geometric realization of that. So let me try to give you one example. And picture is going to be a dual to this construction. So I'm going to have as my starting point two groups, G and H, that maybe give rise to Schmor varieties. Schmor variety H inside a Schmor variety of G. And I'm going to begin being influenced by an integral representation for an L function. So I'm going to have some sort of exceptional modular form, I'll call E, on the group G. And I'm going to integrate it against something on H, maybe some cusp form on H. And say phi of H belongs to some cuspidal representation, say, but that E is something a little more degenerate, like an Eisenstein series. You should think E really means Eisenstein series here. And this should be an expression for an L function. Or an L value of pi. And what I'm really looking for is some kind of geometric interpolation or interpretation of this in the context of these Schmor varieties. So it's going to look something like, what's that? It's some cuspidal automorphic representation for H. H and G are over the number field F. Say. So, simple example, G could be GL2 over the rationals. The corresponding Schmor variety is the modular curve. H could be maybe something like an embedded multiplicative group of an imaginary quadratic field. And I should think of this Schmor variety of H as being a collection of CM points. And this could be an L function for an Eisenstein series, summed over some CM points against a Hecke character, and that would be the L function of the Hecke character. So that would be a simple case of that. And then, so the picture in the analog is that I'm going to, in the Shimura variety, let's say D, maybe in the Shimura variety of G, if I'm really lucky, and the nicest thing, I'm going to look at the D part of the twist here. Remember, now this is QP coefficients. This should be described by holomorphic forms. Most of the stuff in here, if we want something interesting. So maybe we have our Eisenstein series gives us, I'll just go ahead and write the QP of D in there. Maybe the Eisenstein series gives us some line, Galois stable line inside there. I may have to pass, if there's a character involved, I may have to pass to a slightly bigger field than GQ, or I may have to take into account the action of that character. I'm going to look at the dual to the picture I was looking at before. So instead of open cohomology, the open variety, I'm just going to express this in terms of relative cohomology. So I'm going to look. It's just a D. Okay. D is probably for the dimension of the Shimura variety of G in practice. And I said, so it's going to be relative to the cohomology of H. Again, QP of D, I have a map there. And this receives a map from the D minus 1 cohomology of H, but with this QP of D twist. And this is where you know that whatever L value we're looking at, it's not in the range of special values. It's going to be on the edge. When we talk, and this is going to relate to a regulator, which is good because that's usually related to a gamma factor. All right, so inside here we have maybe a map to a Galois representation associated to the pi. So this is the same pi. There's some associated Galois representation. The L function of that Galois representation should be the L function of pi that we're seeing here. And then we should get an extension like this. Some subquotient. And there's a couple of things to ask about this. I mean, first of all, of course, one needs to know that this class is actually in the image of this map. That's usually not too hard. Particularly if D was the dimension of G, then the next degree over is next map over is the D of the Shimura variety of H, but that's too big to have holomorphic classes. Of course, is this non-trivial? That's the big question. So let me move that up so that people can see that. So we want. Well, first thing I might do is a check where I replace QP with, say, the real numbers or the rational numbers, and I think of this as an extension in the category of Hodge structures, and I ask, is this non-split in that category? And in that, you can actually do the calculation, and you see that whether or not it's non-split is actually related precisely to an integral formula like this. That's why I'm sort of motivated by this. So all I do is I just need to find a primitive of this Eisenstein series, which is just another Eisenstein series in the same automorphic representation, and then I restrict that Eisenstein series to H and integrate against the cusp form to detect whether the class was non-zero. So you get an L function. And now, but okay, so maybe we're interested in the classes in Galois cohomology coming from this E. And well, you can actually essentially do the same thing if you're lucky. You can use p-adic Hodge theory. So one thing I should have said is that Tate not only gave us tools from Galois cohomology, but he also, I think, told us that whenever we do étale cohomology, we should never forget de Rham cohomology. And so I'm going to apply the sort of, the B or the D de Rham functor, or the DST functor, or whatever, from p-adic Hodge theory, and I'm going to be able to describe this Galois representation extension exactly as I did the the Hodge, sort of real Hodge extension. Now I have to use p-adic modular forms, and if I'm particularly lucky, I can get an analog of this. I can compute the block-Kato logarithm of this extension by an analog of this, which is computing a value of a p-adic L function. And so I'm also motivated by the constructions we have of p-adic L functions.
Can I ask, is this integral the special value of L or just some derivative? Because otherwise, like you're saying some extension is non-zero.
It depends on which side of the functional equation you end up identifying this with. It's either a derivative, or on the other side of the functional equation, it's just a value. And
But the fact that the extension is non-trivial means something has to vanish. It's kind of
yes, but
using the thing that
yes,
the fact that something doesn't vanish.
like a derivative or a value on the other side of the functional equation. Yes, that's true.
But something else has to vanish.
Something has to vanish. But that's kind of, it's almost baked into the thing. With the integral that I would get out would be the analog of like L1 of chi, but the non-vanishing of say Dirichlet character, but the non-vanishing of that is a reflection across the functional equation of the non-vanishing of a derivative. Then you can be more ambitious and then try to vary the data that goes into these particularly nice classes and see whether you can sort of convert these extension classes into, or organize them into an Euler system. But essentially by varying the character chi. Eisenstein series, think of classical Eisenstein series, there's some characters that go into them. So essentially by varying those characters, you get classes that are defined, whose Galois action involves characters. And as you vary those characters, you get classes over other abelian extensions. For that to be useful, one needs an integral version of this construction. So you need to be able to recognize when these extensions can actually be realized in integral cohomology. And there's some recent advances in integral p-adic Hodge theory that can be used to sort of explain that. And so in fact, you can use this construction to recover all, I think, but maybe a couple of the known Euler systems that have cyclotomic variation. The cyclotomic units one comes from taking the usual Eisenstein series, and the H here is really coming from the boundaries, from some cusps. When I take H to be an imaginary quadratic field, you get the Hecke characters, and you recover the Euler system for elliptic units. If I take G to be, say, the product of two modular curves, so GL2 cross GL2, and H to be GL2, and I take my Eisenstein series on the product to come from two Eisenstein series, I recover Kato's Euler system. But you also get more. So very recently, in collaboration with a now former PhD student, Marco Sangiovanni Vincentelli, we have carried out this construction in the case that G is GSP4, the Siegel threefold that we also saw in the previous talk, and H is the embedded product of two modular curves. The Eisenstein, or this class, is a Siegel-Eisenstein series, very simple kinds of Eisenstein series that we know pretty much everything about. So we can understand these classes. And the map here is the symmetric square, or the adjoint. So we get the Euler. We get the Euler system for the adjoint of a modular form. I should say we've only done the full details in the case of when the modular form is ordinary, but we do recover an Euler system in that case. In this situation, then, this L function, that shouldn't be a surprise. This is the Siegel-Eisenstein series integrated against two cusp forms. This is a famous integral, or example of what's known as the doubling integral formula, Piatetsky, Shapiro, Rallis, and others. And it vanishes unless those two modular forms are dual, and in which case it spits out the standard L function, which is the adjoint L function for the modular form. It's certainly likely that this strategy can be used in many other settings, and I have a student who's working on an Euler system for the triple product of three modular forms using this, and then we're also working on Euler systems for UN1. And I'll stop there.